All right. Today we want to introduce a basic concept in process analysis known as Little's Law. In order to motivate and to give some kind of setting for this story, I want to consider a pretty simple scenario that we see all the time here at Hopkins. So let's consider a walk-in clinic where patients arrive. So each patient will have some associated entry time. Now, when a patient walks into a clinic, in most cases, you're going to have to wait when you first walk in. And I'm going to use the triangle here as to represent a holding area or a waiting room type of arrangement. So patients will typically wait, then they will see some sort of service provider, which may be at the front desk, for example. They typically have to wait again before they see another service provider, which may be a nurse or a clinical assistant. They may have to wait again before they see another service provider, which might be the physician or a nurse practitioner, and so on. So different patients will actually see a different number of resources in this clinic. Some patients will come in simply to make an appointment, so they only deal with one element of our system. Some patients will come in and they just need to do a follow-up visit with a nurse or a clinical assistant. Some patients will come in, they need to see a doctor. Some patients will come in, they need to see a doctor, plus additional lab work and so on. So each patient will have his own unique time in this system and may have his own unique sequence of steps in this system. But what we know is that each patient will have an entry time and each patient will have an exit time. Okay? So if we count how many patients enter over some period of time, we will know patients per hour, which I'm going to write as lambda. So we have an arrival rate. We also know the exit time minus the entry time, which gives me something which I'm going to call cycle time. The time between when you enter the system and when you leave the system is what I mean by cycle time. Similarly, I will always be able to figure out, or at least if I walk in and see, I can count how many jobs are in this system. So my number of patients in the system I'm going to call my work in process inventory. By process, I mean, in this case, you enter the clinic at some point, you exit the clinic at some point. Everything that goes on between those two boundaries, I'm calling my process. That quote process may have one component or it may have multiple components. It really doesn't matter at this level. So what we know, and what Little's Law tells us about this kind of scenario, is that on average, the arrival rate, which I've written here as lambda, times the average amount of time, my cycle time, has to equal something analogous to distance, which in this case I'm calling my work in process inventory. So rate times time equals distance on average. Not for every single moment, but on average these things have to balance out. Now, clearly if we have this relationship, then we also know that lambda has to equal the average work in process inventory divided by the cycle time. And similarly, we have to know that the average cycle time is equal to our work in process inventory divided by lambda. So if I know any two of these elements, I can figure out the third. Now, you may ask, well, how could such a thing happen? Why would I only know two of these things and not know the third thing? So let's consider a couple of simple examples here. So example one, I'm interested in what's going on in this clinic, and I'm going to pay someone to say, sit at the back door and just count how many patients exit this system. So I tell a student typically, sit there for 8 hours and count how many folks exit this system. So the student may report something like number of exits over an 8-hour period was 80. So I have 80 patients over an 8-hour period, which tells me that my exit rate lambda is equal to 10 patients per hour. Now notice here that I'm actually calculating an exit rate, but I'm going to surmise that the exit rate on average and the entry rate have to be the same. Because if the average exit rate was greater than the average entry rate, that would mean I would have negative inventory, and that's impossible. If the average exit rate is less than the average entry rate, that would mean I have an infinitely large pile of inventory, and that's impossible as well. So on average, it doesn't matter if I calculate lambda at the beginning or the end because they have to be the same. Now, let's say in this example again, that in order to figure out cycle time, I'm going to use something like a survey. So I ask the patients how long it took you to get through the system. And let's say my patients come back and say, on average, my cycle time was 1 hour. Well, I know that lambda times cycle time equals work in process inventory, or in this case, I know that 10 patients per hour times 1 hour has to equal 10 patients. Which means, on average, I've got 10 patients within this system. Some of those patients might be waiting at different positions. One patient might be with a nurse, a different patient might be with a doctor, or a different patient might be with a clinical assistant, and so on. I don't know that exactly. I'm just saying on average, I've got 10 patients in this system at any given time. Consider a second scenario. Here I'm going to use my survey again to learn something about cycle time. And let's just say my survey results come back and it tells me that my average cycle time is now 1.5 hours. Okay? Now, I may decide that paying someone to sit here for 8 hours and just count the exits is sort of a waste of a valuable resource. So another approach to this would be to tell my worker, go through the clinic once every hour and just count how many people are in the clinic. So maybe you do that 8 times and you come up with an average number. And in this example, let's say I get something like my average work in process inventory is 10 patients. Okay? I know that lambda has to equal the work in process inventory divided by the cycle time, which in this case is 10 patients, divided by 1.5 hours, right? Which is turns out to be 8.75 patients per hour. Okay, so I didn't know the cycle time. I used a couple of different mechanisms to come up with the other elements. Excuse me, I didn't know the arrival rate, sorry. But I used a couple of different elements to come up with the other parts of the equation. Use a survey for one, a worker to come up with the average work in process, and I can figure out the average arrival rate from there. Let's consider a third scenario. So here, I may decide, for example, that just counting patients that exit the clinic may not be quite the right way to do it. For example, in some settings, a patient comes into the clinic and immediately gets admitted to the hospital, so they don't go back out. So in that kind of scenario, I need to count the patients that enter the system as opposed to those that exit. So let's say I pay a worker to sit at the front door, and my worker comes back and says, my entry rate in this day was 70 patients over an 8-hour day. So I get a lambda is equal to 8.75 patients per hour. And I have another worker go through and count the inventory over the course of the day for 8 times and give me an average value. So he comes back and he says the average work in process inventory is equal to 10 patients again. And again, from Little's law, I know that cycle time has to be work in process inventory divided by the arrival rate, which in this case is 10 divided by 8.75, which works out to 1.14 hours. So, what have we covered here? We've used one fundamental relationship, which applies to any process if we're just talking about averages. And we've demonstrated how if I know any 2 of the critical elements of this equation, I can figure out the third. Key points here. We have not assumed that all of these jobs are the same. We have not assumed that any of these times are deterministic. You can have all kinds of variability here. We haven't even assumed that all jobs have the same number of steps. The beauty of Little's law is that it will apply to this kind of setting. It will also apply when I have variable service times. It will also apply when I have random arrival rates. As long as I know the averages, I can figure out this relationship, and this is a great starting point to figure out what your process is doing.